There we go. Okay, does that answer your question, Jessica? Okay. Balance bridges are really simple. You just have to remember what is the mean by balanced. There's no voltage, no current going through this. Then you can just solve each one as an individual branch. Any other questions about balance bridges? That's basically the idea of how they work. And what we use them for is we use them to detect small changes in voltages or small resistance changes. What is going on now? Something's connecting. Okay. Time constants. Specifically, what part?
I'm lost from the beginning. So. Like I have the equations, but when I start plugging them in, I get confused.
Okay. So let's go through a circuit. Okay, so just a simple RC circuit. We have 24 volts. We have 39 microfarads and 300 kiloohms. So in this question, we're looking for two answers. We're looking for what is our tau and what is our voltage at a specific time. Okay? So the first thing we're looking for, again, is tau, which is the time constant. Tau is simply resistance times capacitance. So to find out what our time constant is, and the reason we know that is then we'll know how fast it's going to take this capacitor to charge. How long does it take for a capacitor to fully charge? 5 tau. That's a T.
No, like not tau, but 5 tau is T time, right?
It would be 5 times your tau would give you, because this is measured in seconds, that would give you the total time it would take to fully charge this capacitor. So in this case, tau is going to be 300K times 39 micro and what our tau comes out to be is 11.7 seconds. So it's going to take 5 of these periods to fully charge a capacitor. So 5 tau is going to be 58.5 seconds. So now the question's asking, what is the voltage, so capacitor 1 has no initial charge, which is also good to know, and what is the voltage of the capacitor at 45.63 seconds? Now we just need to plug into our formula. So the V voltage of our capacitor is equal to the voltage final plus the initial voltage minus the final voltage times e to the negative t over tau. So what we're trying to solve for is this voltage. It's what we're being asked for. So we plug in our numbers. V final is it's trying to charge up and it will get to the 24 volts. We're starting at 0 to E of the negative 45.63 divided by our tau, which is 11.7. We plug this into our calculator, so we're going to get 24 plus a negative 24 times E So we got negative 45.63. We divide that by 11.7 to the negative 3.9. So we go e to the negative 3.9. We multiply that by a negative 24. We take 24 plus this answer. And the charge of our capacitor, or the voltage of our capacitor, is 23.514 volts. Which, if we go back and remember, when we have our 4 tau, that is what percent? Do you guys remember? 3 tau, I believe, is 95. 4 tau is 98.3, or right thereabouts. So even then, we could take the 24 times the 90, what is it, did I say 98.3? And we're at 23.592 as if we went to the full 4 tau, which we're just barely under it. And if we went 4 full tau, 25.59, we're at 25.51. So the answer makes sense to where we should be as far as our ratios. And that is what our question is asking us. Okay? The other part of the question that we could have, let's just take this exact same circuit. Okay? We have everything solved out. I want to know at what time does our voltage of our capacitor equal 10 volts? So we're going to solve for time on this one. We're going to use the exact same values as we did before. This one gave us the time and told us to solve for the voltage. Now we have a voltage. When it gets to a certain threshold, we need that for some circuit to activate. How long is it going to take us from the second we turn it on? So again, we're going to go back and use our formula. So we start with 10 volts is equal to the final voltage. It's trying to charge to 24. We're starting at 0. And there's our formula. So now we need to go through and solve this guy down to where we can get to t. That's what we want to know. So we subtract 24 from both sides. I'm just going to leave the tau as tau until we get down to it, just to save space when I'm writing. So I'm going to take the negative 20 or negative 14 volts, divide it by the negative 24. So now I have, this will drop off. So I've got 14 over 24 is equal to the e to the negative t over tau. That's one of the things we need to make sure is this value over here is positive. If it's negative, we can't take the natural log of it. It's one of those undetermined numbers. So now to get our exponent by itself, we take the natural log of both sides. And we're left with that. We multiply both sides by tau. So we get 11.7 times the natural log of 14 over 24 is equal to time. We'll move the negative side over. And that's our equation to get us the time. Now, there may be other questions on the test as well. What does this come out to be, first of all? because we want time to be positive. In the equation, it takes the negative t, but when we're talking about time, time is always moving forward. So we want our time to be positive when we're looking at an answer.
So does it just become positive like we don't see anything?
Well, we moved the negative over here. We multiplied this side by negative tau. That got rid of that and that. We have to move that across. So how much time does it take for us to get to 10 volts? Four point? That'll change it. Okay, so we had. Kind of like what I did yesterday when I was going off of 27 versus 24. Okay, so our time is going to be 6.3 seconds. So it's going to take it that long to get there. Another part of the question is, okay, we want to know how long does it take to go from 10 volts when it's charging to go from 10 volts to go to 20 volts. Okay, so the next question, so this is our first question. This could be our second question. And the third style of questions that we're going to get is the time to go from
Question is, were you trying to do it at 14 seconds or 10 seconds?
10 volts.
Oh, 10 volts.
Sorry.
How long it's taken to get there?
Yep.
So where did we get the 14 from again?
So the 14 came from our first step right here. We have the voltage of the capacitor, which was 10. That's the voltage we're trying to find the time for. Our final is we're trying to get to 24, and we're starting at 0.
So it's the voltage of the capacitor minus voltage final over voltage final.
Yes.
Okay.
Yes. So in this case, we want to know how much time does it take to go from 10 volts to 20 volts. Well, now we've already solved this first step because we've already solved the voltage or the time it's going to take to get to 10 volts. Now we just plug this into our equation again, only this time we're going to solve for 20 volts. When we get this time, we're going to subtract these two, and the difference is the time it takes for the capacitor to charge from 10 volts to 20 volts. So in this case, if we did want to just look at this like what Zach was doing, if we wanted to create a formula, we have, let's create it. VC is equal to V final plus V initial minus V final times e to the negative t over tau. VC minus VF divided by V initial minus V final, this value right here, is equal to e to the negative t over tau and then we have our negative, so we have negative tau times the natural log of VC minus VF, V initial minus V final is equal to time. I know I skipped a bunch of steps.
Wait, that's our
Time.
the time from 10 volts to 20 volts?
This is how to solve the time for any capacitor. So,
divided by the initial minus V final?
So this would work for any of them. Charging, discharging, doesn't matter. We're charging a capacitor from a value to another value, and we want to know how much time it takes to get to a specific value. So again, we can go through and we can plug these values in, and this is the exact same as we have up here, just without using the values to solve for it. So we plug these in. So we got negative 11.7 times the natural log of 20 minus 24 divided by 0 minus 24. And that will give us the time. So we know that the time it takes to go to 10 volts is 6.3 seconds. So we should, and we know that it takes 58 seconds to fully charge. So our answer has to be somewhere between 6 and 58 seconds. So there's kind of another little double check that we can do. We've given ourselves parameters for maximum and a known value to get there. So when we plug this into our calculator, natural log of 20 minus 24 divided by 0 minus 24. The time it takes is 20.9 seconds.
You have to do that again, right?
This is our second time.
Oh, that is, okay.
Because we already solved how long it takes to get to 10 seconds. Now we just want to know the difference in time going from 10 to 20. So to get to 20 volts, it's going to take 20.964 seconds. We subtract those two. So this answer was it 903? 306. This is the total time it takes it to go from 10 volts to 6 volts, or from 10 volts to 20 volts. So it takes us 14 and a half seconds to go from 10 volts to 20 volts. But it takes us 58 seconds to get all the way charged up to 24 volts. Takes, mine's not quite here. Any questions? This kind of covers all three of the different styles of questions we're going to have on the test. What is my time to get to a certain voltage? Or what's the voltage at a specific time? How much time does it take to get to a specific voltage? And how much time does it take to go from a voltage to another voltage? And that's kind of the three cases that we're going to be looking at when it comes to capacitors. We could also solve for it. Any of these values. If we wanted to know what value are we trying to charge to, and we took this long to get to this value and this is our tau, we could do the same thing. What's the final voltage I'm trying to get to? Which sometimes you'll need to know. What voltage does this capacitor have access to? And how long is it going to take to get there? Okay. Any questions about time constants? Okay. There could be, yes. Hmm? The angular velocities? Might as well look at those two. All right, so series parallel unknown R3. Okay, there's going to be our circuit. This is R1, this is R2, this is R3. So we're given 32 volts, 22 ohms, 30 ohms, and R3 we're given a current of 779.221 milliamps. So with this, we don't have any information. We're three-legged on all of our options to go through these. We don't have another piece of the puzzle to solve for any of the voltages, total resistance, total current, anything like that. So at this point, the easiest thing to do is we're going to use Thevenin, because this allows us to remove something from the circuit and not worry about it until the end. That's kind of one of the other ideas of Thevenin, is it allows us to kind of cheat our circuit. Gets rid of something. So what we want to pull out is R3, because that's one of the values that we don't have that we need, but there's no other way that we can pull something out and be able to solve the rest of the circuit. It won't work. If we pull out R1, we'll have an open. We'll have zero current. We'll have nothing we can calculate. If we pull out R2, well, that's good, but again, we're still left with this guy. Okay, so the only option we have is to pull out R3, the one unknown that we don't have. So when we pull it out, we now need to solve for our V Thevenin, R Thevenin. We're going to work backwards. So on these guys, use Thevenin's theorem. So our V Thevenin is going to be the voltage from point A to point B. And in this circuit, that voltage is the voltage drop across R2 with R3 removed. So we've got 22 ohms and 30 ohms. So we've got 32 volts multiplied by 30 over 52. So we just use voltage divider to solve for this guy. $18.462 volts. You good there, Seth? Or are you working on a different one? Okay. You went for R Thevenin first?
Yeah, sorry.
Okay. No, that's good. I just saw confusion and I wanted to make sure we were if it was something I did or something else you were working on. Okay. So does that make sense, Simon? So we've got 30 and 22 in series. Add them together. Okay. So now our R Thevenin is the resistance that we see from point A to point B. We short the supply to get it out of there. So all we're left with is R1 and R2 in parallel. Do what? Add them again? No, this one we'll use the reciprocal method to solve these guys. So R1 and R2 are in parallel for our R Thevenin. For the V Thevenin, they were still in series. So we end up with the R Thevenin value, 12.692 ohms. Yep. Sorry, we're still trying to figure out things with insurance, and that's what kept popping up. So, yep. So then we throw it into our Thevenin circuit. So we have our V Thevenin is 18.462 volts. R Thevenin is 12.692 ohms. And we put R3 back in its place. And we know that we have 779.221 milliamps. The nice thing about Thevenin is this is where it combines our original circuit back together. Whatever's going through this load resistor is the answers for this point in our problem. So we can work backwards with that. So we know we have, oops, that's one too many sevens. We've got 779.221 milliamps. So now we know in this circuit we have this much current. Well, these two guys are in series, so the current is the same in both resistances. So now we just have to find what's our voltage drop across the R Thevenin, subtract that from our source, and then that's going to give us the voltage that we have left across our resistor. Once we have that voltage, we can then use the current to solve for what R3 is. So this V R Thevenin is equal to 12.692 ohms multiplied by the 779.221 milliamps. Yep. So this guy is dropping 9.89 volts out of our 18. VR3 is equal to the V Thevenin minus the VR Thevenin. Again, they're just labels. So we have 18.462 subtracted from the 9.89. 8.572 volts being dropped across R3. Now we can take that voltage and put it back into play. So the 8.572 volts divided by the current, 11 ohms. So we come back to our original circuit, we plug everything back together, and now we know that we have 11 ohms being dropped across, 11 ohms of resistance here, and we have 8.572 volts across this guy. And so the things we want to solve for is the first one is we need to solve for the value of R3. Then we need to solve for the voltage drop across R1, the voltage drop across R2, and our total current. So what's the voltage drop across R2? 8.572. What's the voltage drop across R1? 32 minus that value. Because those guys would combine together, they're going to have the same voltage, and whatever's left is going to be what's dropped across R2. Okay, what's the current in your head?
285 plus 779, which is
Close. It is a lot of amps. It's because we have very, yeah, 22 ohms is nothing. Okay? So if we have 1.65 amps coming down and through here as our total, we have 779 splitting off. How much do we have going through R2? How much did we have? 285. Okay. Does that make sense, Simon? Okay. Biggest thing, like I said, is you Thevenize it, and then you know one of the parts when you get down to your Thevenin circuit, That's the same current here. You find the voltage, subtract your voltage from your Thevenin voltage. That is the voltage and the current through that resistor. You can then solve for the resistance value using Ohm's law. The voltage of R2 is our parallel laws, and then our voltage of R1 is using our series laws.
You know, if we didn't write these in engineering notation, and you actually had to write out all the zeros, I'd probably get a whole lot more of these wrong.
That's one of the reasons why we use this. It makes things a lot more accurate.
Brody,
Yes.
I passed all the time constant quizzes.
Good.
Now I just have the final, the test, and one quiz. It's come together. It's making a full circle.
I don't look.
No.
I have to laugh so hard at this one.
Yeah.
No, I was like, that's okay.
I lost it.
Kind of cute though. Kind of cute. Brody, let's get matching tattoos.
I think
I'm
you
good.
asked him that before.
I did, but if I just keep asking him, then it's problem.
You would think.
That is how.
I already answered that.
Okay. So troubleshooting, we'll kind of start off simple. We're going to have three things that we can have. If we can try and make four, we'll see. Okay. So the idea behind the troubleshooting is we're going to have four sets of values. Just trying to come up with the troubleshooting question in my head's a little hard. So we're going to kind of work it backwards. Okay. What are all the possible scenarios that we could have in this circuit? We'd have shorts and opens. Okay. Or it works. Okay. So with this configuration, we've got R1, short or open. So there's two combinations. We have R2, could be short or open. We have R3 that could be short or open. So there's 6 combinations that we have. However, one of these combinations we can just simply lump as either or. Okay? And that is if R2 or R3 are shorted together. Either one of those are shorted, we're going to get the same effect. Okay? So our options are normal, R1 short, R1 open, and then we have R2 open, R3 open, and then R2 or R3 short. Because they're gonna react differently. In this case, they would be the same because they're the same values. So in that case, there you go. There's another one. Because we have those same values, if either one's open, we're going to get the same values. Okay? So we could swap this down even farther. Okay? So now we have 5 conditions, 4 failure modes, and 1 normal mode. So the first thing you should do is when you're troubleshooting a circuit is figure out which one or what is my normal mode. Okay? Okay? So the different measurements that we could have, let's look at currents. So let's go with I total, IR1, IR2, and IR3. Okay? So in our normal operation, what would our total current be? 100 milliamps. How much current would be going through R1? How much current is going through R1? All of it. Okay, so in this case, we could probably even get rid of this column because I total and IR1 are going to be the exact same things. Okay, how much current's going through R2 and R3? 50 each. Okay, so if R1 was shorted, what would the current be through R1? If R1 is shorted, what's going to be the current going through those points? All of it, but it's going to change because how much resistance is R1 now? 0. So now, how much current are we going to have going through this guy? So how much total resistance we've got? We've got 50 ohms and 10 volts. If we were, because how would we measure current through R1? We'd put our current meter right there. So we'd see 200 milliamps. Because R1 is shorted out. Because now we're missing that 50 ohms of resistance. Okay? How much current do we have going through R2 and R3? 100 each. This is why I chose these values so we could just do it real quick. Okay? If R1 is open, how much current is going through R1? 0. It's open. Only voltage. Okay? So we're going to have 0 across the board. Okay? What if R2 or R3 is open? What's the current we're going to see through R1? How much total resistance do we have? 150 ohms. Okay, how much current do we have going through R2? Yep. And actually, let's just say one thing that we could do is if we're measuring current, do we get back to each one of them can be open? So when we're measuring current, now we've gone through the R2 or R3 open condition. Does that change the options for us? Because is R2 and R3 going to both be measuring 66 milliamps or 66.6 milliamps? It'll be either or. So this actually turns back into our two options. And the only difference being okay? So what we're doing is we're just creating our chart. Okay? So now the next one we have, this one will not matter. R2 or R3 short. Doesn't matter. If either one of those shorts out, what's going to be the resistance total across our parallel branch? 0. Because if we short it, we have 0 in parallel with 100 in parallel with 100. It's going to be 0. Yep, it completely bypasses it. So now, if R2 or R3 shorts out, how much current do we have going through R1? Okay. How much current would we have going through 2 or 3? 0. Okay. Okay? So, now that we have our chart created, what you guys are going to get in the test is going to be a couple of these options. You're going to get, I think you're going to get one that's a normal operating condition, and then you're going to get 2 or 3 of these other cases. Okay? So if you had this chart, what am I doing grabbing that eraser? It's in my hand. Now we didn't have the conditions. This is how the question would be related. Okay? As we're going through these, and of course they're going to be in different orders, what's our normal operation? Well, let's solve for it. Okay? Look at the values they're looking for and solve for those values. That's going to be normal operation. There's one of your answers right off the bat. Plus it gives you a baseline. Okay? So now we go through and then we say, okay, let's say we have this guy right here. So we're given this one. And that one. Okay? So the first one's our normal operation. Because we're able to calculate it, okay, hey, we have the total resistance, we have everything working, that's our normal operation. Okay? If we're reading 0 current through everything, what possible conditions could we have? Because we can only choose one option. R1 is open. There is no current flow whatsoever in the circuit. Because again, if one of these guys are open, we're still going to see some resistance, and that's going to change from our normal. Okay? This guy, we're seeing 66 milliamps going through R1, and we're seeing the same going through R2. So if they're the same current, what does that mean? They're in series. How do we get R1 and R2 in series? Opening this guy. Because if this guy's gone, now those two are directly in series. So kind of look for those clues. If you have same currents, they're going to be in series. If you have the same voltages, what does that mean? You're going to have things in parallel. Okay, the last one, we have no current going through 2 or 3, which means what? And we have current going through 1, which means what? Means a short. There is something basically connecting from here to here and bypassing that entire part of the circuit. So that's the troubleshooting portion. Really, all we're trying to get you to do is to think, what happens if I have these conditions and I'm looking at these values? So a lot of times you'll either get voltage readings or you'll get current. Sometimes you'll get a combination of both of them.
One thing that I did on this last one, I believe, is like I put it as when I was like drawing it out and everything, and when I was trying to put like R2 and R3 in parallel, it's like, okay, if someone's open, I did like 99.9999 like times 10 to the third, whatever, and then put it in parallel with the other one, and then like gave me some like astronomical numbers too. So it's like, okay, that was a visual.
Yeah.
Like, saying it. Or if it's like, because it won't take 0 if you do the inverse. So you have to do like 0.0001 or something. Just something really, really small.
Yeah, that's the other way you can do it, is because you're going to have some resistance with a piece of wire, not much, but there is going to be some there eventually. And that's what we're going to find out with inductors, because all inductors is wire that's been wrapped around a core lots and lots and lots and lots and lots and lots of times. So you're going to have, 75 feet of wire in a little package this big. Does that make sense, though, for troubleshooting? Okay, that's the idea. Think about what is going on. Okay. Last two we have. So angular velocity. Angular velocity is basically how many degrees or radians am I traveling as I'm going. Okay? So as I'm spinning around in a circle, I'm going so many times a second. This is my frequency. Is your cycles per second. How many times am I going all the way around? Now, if I want to know what's my angular velocity in degrees, it's your frequency times 360 degrees. Because if I'm traveling at 60 hertz, which is 60 times a second, For 1 second, I've gone 360 degrees 60 times. So how many degrees have I traveled? So you just multiply those together. Yeah, 60 times a second multiplied by 360 degrees for each complete cycle. And that gives me how much? 21.6? I've gone 21,600 degrees in 1 second. I've gone around this loop 60 times. Okay, how many radians? Times 2 pi. Now the answer could be given you in terms of pi or just a value. So let's solve for them. If we're still at 60 hertz, I've gone 120 pi rads per second, or I can carry that out to a full decimal. And that is 60 times 2. So I've either gone 120 pi rads or I've gone 376.99 rads. Now, 1 radian, or like a circle, it's 2 pi rads. So if we take that apart, so 1 radian, or 2 pi is 6.28. So to give you kind of another idea, we can carry that out into its decimal equivalent. So that's all angular velocity is. How many degrees or how many radians am I traveling based on my rate of speed? Okay. What if I had something that was cycling, let's say it was going 4,200 RPM. It's like the engine of a truck. You got 4,200 RPMs. And we want to know how many degrees are we going. What's our angular velocity of 4,200 RPM? Mm-hmm. 4,200 RPM, and I want to know its angular velocity in degrees. How much did you say it was? Megadegrees per second. So I'm going 1.5 million times around in a circle every second, or every minute. Okay, so that's the other thing we got to look at. So our angular velocity, we want in degrees per second. This gives us degrees per minute.
So it's 25.2.
How much?
25.2.
So that's kind of the tricky thing is. You're not going to see this style on the test, but I'm showing you can still, it's the same idea. You've got something moving around at 4,200 rotations per minute. We want that down into a frequency, which is number of times per second. So we divide our answer by 60, multiply it by 360, and then we end up with this total value of degrees per second. That's all we want to know with angular velocities. How many degrees am I traveling per second? How fast can I travel? Because that's how a lot of motors are rated. They're rated in how fast can you go before they blow themselves apart. So obviously engines can handle going this speed because they do it all the time. There's a lot of rotations. Yeah. Yeah. Physics class, you might need to know that. Just saying for next semester.
It's crazy because when you change like one thing in the engine, it's changed all of them, or else the thing would just start breaking. Like you change like your compression or your like cylinder volume, but you don't change your like crankshaft or like the arms, the piston arms. They'll just snap one day.
Yep.
Like this
because things are moving way too fast. Okay, the last one that we have is we want conversions between degrees and radians into degrees, because we're going to use both of these guys. So remember, 360 degrees is 2 pi radians. Okay? So when we want to convert these guys, if we want to go from degrees into radians, so we have 360 degrees, sorry. We've got X number of degrees over 360 is equal to X number of radians over 2 pi. And so let's say we have 15 degrees. So we're going to solve for how many radians we have. So we have 15 times 2 pi is equal to X radians times 360. We divide both sides by 360 to get rid of it over here. So we have 15 pi over 180. Is equal to the X number of radians. So basically what it comes out to be, it's the number of degrees times pi over 180 to go back and forth. So this is our conversion to go from degrees to radians. Divide your number of degrees by 180, multiply it by pi. That's degrees to radians. The other way is if we have, say we have 7.5 radians over 2 pi is equal to X number of degrees times 360. So we have 7.5 radians times 360 is equal to 2 pi times X degrees. All I'm doing is cross multiplying across these things to get rid of the fractions. Divide both sides by 2 pi. We end up with our number of radians times 180 over pi. So our ratio flips. Because the radians will cancel and we're left with degrees. That's radians to degrees. Okay.
Is that it? Are we done?
Yes.